Nice.
Hello, everybody. Sorry for the delay. Today it's our great pleasure to have Michael Beverland from IBM Quantum. Michael is an expert of fault-tolerant quantum computing, and today he's going to tell us about the new design. So, Michael, the stage is yours.
Thanks. Yeah, so I would like, even though this is kind of a recorded online talk as well, for people to interrupt if there's anything that we want to discuss. I think this is the second talk on this topic. Patrick gave a talk on the same paper last week, and we planned to cover slightly different aspects of the work. But I think the fact that we are doing it that way lends itself to diving into more details. So that would be good if you could interrupt on things you want to know more about. So the basic idea, if you were at Patrick's talk last week, is as follows. We have a goal to build ultimately a fault-tolerant quantum computer that will be large enough to solve big problems. So potentially factoring large integers, a la Shor's algorithm, but also potentially doing physics simulations that are of interest in the highly entangled regime, and many other problems. But these require very, very large computations, and therefore very, very large quantum computers, which are fault tolerant and fail very, very rarely. So it's not easy to do this. And in this talk, I'm going to explain a proposal that's based on quantum LDPC codes. And so we'll kind of run through the following list of things during the talk. So the first is why quantum LDPC codes. These are not the surface code, which probably you've heard more about in the past. So I'll explain a bit about the motivation for that. The TLDR will be that we need long-range connections, which makes them harder to build, but we think it's worth it to do that. And so I'll explain a bit about how IBM is building long-range connections in order to be able to build these quantum LDPC code-based quantum computers. And then we'll talk about how the logic actually happens in the machine, inside the error-corrected logical qubits. And then I'll zoom out a little bit and explain what you can do with the resulting quantum computer and how it works. And then I'll kind of highlight and come back full circle and highlight what the difference between if we had done this whole thing for the surface codes would be, why we do it. Okay, so quantum LDPC codes, like the surface code, each qubit is touched by a bounded number of checks in these formal definitions. Also, each check touches a bounded number of qubits, also property of the surface code. However, the surface code only requires these checks to be local, geometrically local on a 2D grid, which is it's a very nice property to have. LDPC codes relax that constraint. And I don't expect you to read this, but the motivation for us to switch to quantum LDPC codes from the more established approach of surface codes is that there has been a flurry of theoretical research in the last few years that show how you can do things with quantum LDPC codes that you can't do with non-LDPC codes, with just local correct connections, or the things that you could do, you can do much better. So just for illustration, I would like to show the surface code and then the gross code, which is going to be the simplest code that we use in this proposal. But they're actually very, very similar. So I'll start with the surface code and then show what's different. So in the surface code, everything is laid out in a grid, a 2D grid like this. The dots are qubits that will host the stored information. And you note that I didn't put them on all of the sites of the grid. I only put them on half of the sites. We need the other sites to put other qubits, which don't host the information, but they're just there to detect errors in the system. And so, for example, what is meant by an X in this picture? Yes, I'll do this for here. So what's meant by an X is that this checks these 4 adjacent qubits and measures the tensor product of XX, XX on those 4 qubits. And if that is not a +1 measurement outcome, that's flagged as there having been an error in one of those 4 qubits. And by not measuring each one individually, it doesn't collapse the entire state into single qubit states, and so it doesn't affect the stored information. So hopefully this is fairly familiar to people. There, I drew the X on the X's first. There are also Z type checks of the same flavor. And you can, so we're not at the gross code yet, but you can put this on the torus. And in fact, the toric code predated the surface code. So if you were to put to kind of tile the torus rather than like a square with this, then you pay for that by requiring the long-range gates. If you were trying to implement this on a chip, you now have to build these long-range gates which connect around the back of the torus and over the top of the torus. But you get an extra logical qubit for that. So you could argue whether it's worth it or not to do so. The original motivation of the surface code was that you didn't have to have these long-range gates on 2D. The gross code is a similar generalization. All that you do to get from this toric version, the toric code, is now instead of just doing x, 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 we do x, 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 x. So we have weight 6 checks, and they are long range now as well. So, and this is tiled everywhere. So, this is the same, like that. So there's translation symmetry in the torus of this model. But this buys with the same number of qubits, physical qubits on this torus. This buys us 12 logical qubits now rather than just having 1 or 2 if we had the toric code. Yeah.
In terms of choosing the long-range connections, like, is there flexibility you get with this, or is this kind of like the optimal way to do it?
It's a good question. So this particular code was discovered by a numerical search over lots and lots of long-range connections, and a list of codes that had good properties were kind of extracted from that. Since doing that, we started to see more structure, but that is not, it was not obtained originally that way. It was, these codes were obtained by numerical search. And there are other codes with other properties. For this particular size, this is the best that we are aware of. Okay, so the code I had drawn on the torus, but I'm now flattening it out, so the left and right are identified. But the point is, I'm trying to explain a little bit more about how you would actually implement this in practice. You can't, with almost all hardware platforms, directly measure a tensor product of 6 Pauli operators non-destructively. So how do you do that? Well, you break that down into a small circuit of 1 and 2 qubit operations that you can do on most hardware platforms. And this is kind of just an illustration of how that works in this particular case. So if you want to measure the check associated with one of these pink squares, that's an X check now, then you just do a C0, a sequence of C0s that couple to all of the qubits in the support. And you do this little gadget where you prepare in a plus state, you apply 6 C0s to the support of the qubits, and then you measure out in the X bases, and that implements exactly the tensor product of 6 X's. So you do this in parallel for all of these stabilizers, you get all of the outcomes, and this is how you perform error correction with this system. So if we pick 2 codes in this family, the one that I've shown here, the gross code, it has 144 data qubits and another 144 of these colored ancillas that are used to measure the stabilizers, so 288 in total. And you can just do simulations of these codes and see how well they would perform in this model where we individually are doing 1 and 2 qubit operations. And you get these curves like this. On the x-axis, it's the probability of any one component in your circuit failing, like a C0 between a pair of qubits or a measurement on one of the checks. So the probability of anything in your circuit failing is P, and then the probability of some logical failure in the encoded information is what's on the y-axis here, which we call PL, P logical. Yeah.
Sorry, I have 2 questions. One about the previous slide.
Sure.
What is the difference between the R qubit and the L qubit?
So it's really for mathematical convenience. And yeah, I would say at this level, it's not really that important.
I see. But they're all data.
They're all data. All the R and all the L are data. Okay. But the code has some structure that we leverage for this from this R and L.
I see. And also for this plot, right?
Yeah.
If I look at the surface code, similar plot, it's
Yeah, I'll
actually
just
on the
click
cross-
this so that we can see.
Thank you. Oh, yeah. I remember in the surface code, there is a kind of a critical P.
Yeah, and there will be for every code.
For every
probably.
code, I see.
So we just don't go as far. You can see
I
we
see.
stop on the y-axis before 1 and
Yeah,
stop here before.
I see.
So that
Yeah.
crossing will come just a bit above 1% for the surface code.
I see.
It depends on the details of how you implement these things, but it's about 1% for the surface code. It's about 1% also for these codes.
I see.
Yeah. So basically, if you are below 1%, then if you don't have any constraint on system size, there's a size you can use to do whatever you want. If you're above 1%, then don't use error correction.
Right.
You can't really do much. So yeah, the point here is that the code that we were just talking about is this red line. If you just copy the red line and compare it with the surface codes, you get comparable performance. You're kind of sandwiched between these two. But the number of qubits that you needed to pay for the gross code to encode 12 logical qubits is an order of magnitude below what you need with the surface code. So that's why we care, basically. There are other advantages too, but this is primarily the reason. It's an order of magnitude in space reduction. Okay, so we need long-range connections in order to be able to implement this. I want to talk a little bit about how that's being worked on at IBM at the minute. So some of the stuff I'm going to talk about here are things that have been already built and tested, and some things are things that are kind of planned and in the works. So the idea is that we have a couple of different categories of coupler that we are considering. We're using superconducting qubits, so we have the qubits laid out on chips, and couplers that are not nearest neighbor but within a chip we call C couplers in the chip, and then couplers that are longer range than that and go between chips, so superconducting qubits in different chips, we call L couplers. And this will be relevant because you can't fit an infinite number of qubits on one chip. So if we want a really large system, we need lots of chips, and some of these codes, roughly speaking, we're going to try and build as much as we can of each code inside a chip, and then we'll need to connect chips together to have multi-qubit operations. So the current architecture that you can just use right now if you want, if you go online, is like this. So it's quite low connectivity. It's certainly nearest neighbor. It's actually less than nearest neighbor connectivity in 2D. And then what is being worked on at the minute is very high connectivity. So degree 6 connectivity, but lots of long range connections as well. And this will be expressive enough to be able to implement these. Yeah.
So in the Loon architecture,
yeah,
a lot of intersecting lines. Am I supposed to read this as kind of like a top-down view of a 3D?
There is some layering that is required in order to build long-range connections. So these lines do not physically intersect one another; they kind of pass over one another, and it's possible to do this in a very small number of layers. And there's trade-offs and details and exactly how you do that, which fortunately I don't even know enough about to violate any confidentiality. But yeah, it's a good question. They're not passing through each other physically. So things that have been done already and tested are not this full device where you have degree 6 connectivity, which is higher than the currently publicly available devices. It's not degree 6 connectivity and long range connections, but we've done high degree connectivity and we've done long range connections, and they have not been integrated in a public device yet and scaled to large enough sizes to run these codes. But that's kind of where we're headed. But this has been implemented, and I don't know if we were paying attention during this. I should have called attention to it. But the regime that we would like to operate at is around 10 to the minus 3 physical error rate. 10 to the minus 4 would be even better, but it just depends on how good we can get our hardware. But that's kind of typical of what we are anticipating to be able to run, is the 10 to the minus 3 error rate regime. And just to clarify, that's for everything. So if your measurement is 10 to the minus 2, then you're not 10 to the minus 3. 10 to the minus 2. So the worst gate or operation that you have between preparation and measurement of 2-qubit couplers is P. So we hope that everything that we have is at least as good as 10 to the minus 3. Yeah, go ahead.
Are there opportunities to mitigate specific kinds of errors, like if measurement has a bigger error rate?
There are flexibilities in these systems. So yes, there is room to do a little bit of tweaking. The analysis that we perform in this paper assumes that it's uniform across the board. When you do more nuanced analysis, you can find that there's different kinds of codes or different precise ways of implementing them will allow for worse performance in some gates than others. But I would say you shouldn't be assuming to get an order of magnitude worse in some than that. But maybe like, a factor of 2 or 3 probably. For example, in order to implement these codes, we repeat measurements, and at a kind of back of the envelope intuitive level, the reason for that is because the measurements themselves can be wrong. The measurements are supposed to detect errors happening on the qubits, but sometimes the measurement, performs an XX, like it performs this check measurement, and it's supposed to say that there was an error there, but it accidentally says that there wasn't, because that could go wrong. The measurement can go wrong too. So we repeat the measurements, and that kind of, in a statistical mechanical kind of sense, builds in enough redundancy to fault tolerantly store the information for, in principle, an arbitrary amount of time. But the amount of repetition that you do gives you some control to handle worse memory or worse measurement error rates and things like that. So yeah, there are some things you can do.
What's the current state of the art for this worst case? Like, if I use an IBM machine now, my worst operation on my worst qubit.
What is it at the minute?
Yeah, how far are we from 10 to the minus 3?
That's a good question. I don't know the exact answer to that, but I don't think people at IBM are fundamentally worried about this. Yeah, I mean, they want to do 10 to the minus 4.
Sure.
And right. But yeah, I think that's what I would say. But I don't think that there's a lot of concern about not being able to get below 10 to the minus 3 for everything. It's like you said, there's trade-offs that come in. You want more measurement, then you should measure for longer. That slows down your computer. That means that other noise processes can build up. So there's always some knobs to play with. But okay, so the point I wanted to make here is that in these in these high degree connectivity experiments that have been performed, the error rates are in the 10 to the minus 3 range already. So it's pretty promising that having high degree is not going to kill the system. And the same is true of long range connections. This is in-chip, these C coupler long range connections that we would need to build these codes. They also are in the 10 to the minus 3 range. Some of them are actually pretty large that would ballpark go the whole way across a chip. So that's pretty promising too. The L couplers are a bit worse still, but they're kind of, I don't know what happened there. They're roughly 10 to the minus 2 is kind of the observed error rates that are being achieved currently for these chip-to-chip connectors. And it's possible that if that was not able to be improved, we would have to do something about that at the error correction level. Do some entanglement distillation or something like that between chips. So there's ways around that. Okay, so how do we perform logical operations? This is going to be quite high level, but the error correction world is kind of the world that I live in. So if people want to talk about more detail, then I'd be very happy to do that. Ballpark, there are 4 main ways that we know of to implement logical operations on the information stored in codes. The first is you can essentially think of as exploiting the symmetries of the code. So remember that I told you earlier with the gross code, it has translation symmetry on the torus. That means if you literally moved every qubit across one and up one, and, or across two in the grid, you would get the same code back. And doing that actually implements a logical operation on the 12 encoded qubits in the code. So if you can move your qubits around, then you can induce some logical operations. There's other operations too that can be formed from these kinds of on-site symmetries you can think of, if you think of it as a kind of lattice condensed matter toy model. And there are other approaches too, code deformations, which in some sense are kind of like mapping to a different code. And that process of mapping to another code can induce a logical operation. And then there's other approaches too. The biggest one that we use in this work are lattice surgery operations, which I'm going to explain now. Yeah, this is just what I already described, which is the symmetries. So if you move the qubits along these edges in the graph, then you get the same code back, and that induces some logical operations. So that induces unitaries on the encoded information. So lattice surgery is an approach that was developed more than 10 years ago now for surface codes. And I think it's quite intuitive in surface codes, so I'll explain it in surface codes and then kind of gesture at what happens in the case of LDPC codes. The idea is here at the start, we have two surface codes that are completely disconnected. So they store each one logical qubit. And you could have different shapes of surface codes. So you could have a surface code that is not a square like this, but is a rectangle. And that's what this middle picture is. And that stores one qubit as well. And what a lattice surgery operation is you start with a pair of surface codes, you join them, which eliminates one qubit. And what's actually happening there is it induces a logical XX measurement on two qubits and projects out on whatever the answer is. And that's where the qubit goes. It gets measured out. And so that's the state of this middle piece. And then you break them apart again, and now you have two qubits again, but you've measured logical XX between them. And this, like a CNOT, couples the two qubits. So this, you could use this to produce a bell pair, for example, between these two patches. And so the bread and butter of surface code computing is this, where between patches of surface codes, you're all the time just joining and separating patches and inducing these two qubit logical measurements. Yeah.
Is the joining, like, I guess at the hardware, is that done by the L couplers?
So in this case, everything's 2D local for the surface codes. So this is just an example to illustrate. It's not actually part of what we do directly. But in surface codes, you don't need that. In order to connect these two codes, which happen to be together, all you need to do is here, this is an XXXX measurement, and this is a ZZZ measurement. What you need to do is you need to start measuring ZZZZ here, which is not initially a stabilizer. So this measurement that you apply, it will actually have a random outcome. And you do that for all of these edges, for all of these new checks here to build the rectangular code. And it just kind of magically turns out that what you're measuring is the XX logical operator for these two codes. So whatever random answer you got is the projective outcome of your logical XX measurement. And that's how this works for surface codes. And for LDPC codes, it's kind of intuitively very similar, but we don't have this nice visual picture. You have the code kind of represented down here in this plane, and there's some logical operation. So it's some logical operator, like you have 12 logical qubits, so you want to measure, say, x1, logical x of the first qubit, and stored in your code. Then what you do is you get some other system, which is essentially representing another patch that you bring next to your system, and then you couple them together, and then you split them again. And this process will induce the measurement of that logical x1 operator, your first logical qubit. So in order to do this, if we kind of have a glance at this schematic here. The picture on the right is probably the easiest one to see what's going on. The code that we started with, which is extremely pixelated, sorry, is represented by this torus, and it stores these logical qubits. And then the additional stuff, the additional qubits and connections that we need in order to induce this measurement comes from this up here. Okay.
And these extra things, and also the measurements, induce, say, 2 qubit gates in among the 12 logical qubits. And
very, very good question. So what I described a minute ago was, let's say, measuring out the first of these 12 logical qubits in the X basis. That's one thing you can do. Another thing you can do is measure X1 tensor X2 on 2 logical qubits. And so what we actually do with these codes in this proposal is we sacrifice one of the 12 logical qubits as what we call a pivot. And we just prepare that in another state, and that allows us to induce a unitary on any of the other 12 qubits by measurement.
Okay.
So, I mean, I would have to draw a little circuit, but the idea is if I prepare a qubit in the 0 state, one qubit in the 0 state, and I have another qubit that I want to apply a unitary to, I can measure I can measure XX on those two, and I'll get a random outcome. And this will be a Clifford operation on the other qubit, like a unitary. And so you use this gadget to essentially build many, many unitaries.
And the CNOT can be built similarly? Or
So a CNOT between a pair of these two, you can do it, but you need multiple. So
you mean multiple pivot?
No, you need one pivot, but you need to measure XX between you need to measure, this is how you do it for a CNOT. You have one pivot and 2 qubits, the control and the target.
Right.
So you prepare the pivot in the plus state. You measure ZZ on the control and the pivot, and then you measure XX on the pivot and the target, and then you measure the pivot.
I see.
And that induces a CNOT.
I see. Okay.
But yeah, it's very specific, but you can probably tell the fact that I know this, that this is the kind of thing that we often are kind of thinking through. And yeah, it's kind of burnt into memory. Yeah, go ahead.
What was the motivation for picking lattice surgery over the many other listed ways to do multi-qubit operations?
What can we do? So this is kind of the catch bag of techniques that we know how to implement in anything. And we will use the cheapest and easiest approach that we can. So lattice surgery is the best that we've got right now. And there's a lot of work going into seeing if we can have better lattice surgery or if we can have better other approaches.
And when you say best, to what extent is that motivated by your hardware platform?
Not, I would say. It's a big open theoretical question. What's the best way to do logical operations in these kinds of codes, irrespective of hardware? So we do as much as we can with symmetry, but that only gets us so far. Yeah. Okay, so just to kind of we've kind of talked through most of this, but the idea is that you perform some logical measurements on a pair of qubits. One is the pivot. We now have discussed the detail, and the other is some other logical qubit encoded among the 12. And in practice, this is implemented by some physical circuit on all of the actual qubits in the hardware. So this is like under the hood how you do it, and it's complicated, but it's all mapped out, and we can write down what those circuits are. And then another thing that we need, of course, is we can't get away with a full quantum computer of 12 qubits or 11 now that we've sacrificed one and made it a pivot. So we need to have modules of these codes, each of which is storing 11 usable logical qubits, and they're coupled together. And so to do that, we have another lattice surgery, which is similar to what I could describe before, but now instead of us just having one code and something on top, we actually connect them to others. So this is a very, very simple illustration of what I mean by that. Is this connection here is going off to something else, which looks like this, which is over here. And those also have some detailed under the hood circuit to implement them. There's another thing which we didn't discuss, I won't really discuss in detail, which is everything that I've described implements what we call a Clifford operation, which is not universal. And for universal quantum computing, we need something which is not Clifford. We have a separate module that we use to produce T-states that are consumed by these Cliffords to universal quantum computing. Okay, so I want to kind of zoom out now. These are the things that we've discussed. So we have this place we produce T-states that I didn't really go into. And then we have these connected modules that we can apply unitaries inside using these symmetries. And we can apply these 1 and 2 qubit measurements using the pivot and the ancilla, or this system up here. And then we can couple them together by like XX measurements. So this is rich enough to do universal quantum computing. And yeah, there's various components that go into that. And once you have all of this planned out and all of the circuits designed, you can kind of count up how much this would require, what hardware would this require to build. And I don't want to go really into too many details on this, but just the rough idea here is that if C are the code qubits, then for the gross code by itself, just this piece, you need about 300. And if you want to include this piece in your accounting, then that's another 100 or so on top. And then connecting them up takes more qubits as well. And so that's another 20 odd. And then you also need to account for the factory, which is these numbers down here. For different regimes, you use different factories. So yeah, and we need these L couplers between chips. So what I'm imagining here is that this is in one chip. So that means ballpark 1,000 for this proposal with the larger code, 1,000 qubits per chip. And for the smaller version of the code, a few hundred, maybe a bit less than 500 per chip. So these are big numbers, but that is currently the reality. And of course, we're working to achieve those numbers in hardware and to reduce the requirements in our designs. Okay, so probably if you were able to see Patrick's talk last time, this kind of picture is likely to have come up, and I won't go into it in too much detail. But what this is all of these operations that we've described now are the operations that if you trust that we can build this machine and make it all work in the way that I've described, these are the operations that you would be able to run. So if you wanted to run a circuit, then your circuit would look like this, which is important to bring up, I think, because it's pretty different from the kinds of circuits that people tend to think about without fault tolerance. And so if you're designing an algorithm that's going to run, then ultimately it's going to have to run on something like this. That's what it's compiling down to. And if you're designing an algorithm to run at a logical level on some fault tolerant hardware, then I think it's helpful to know that this is the kind of thing that's going on under the hood, because you might actually design a very different algorithm. Okay, so each of these different operation types are the things that we've already discussed. And in order to predict how this computer would perform for real large algorithms, we need to simulate these and see how good they are. So this is just a sketch of the results that you get when you start trying to simulate these and varying this error rate P for each of the components at a physical level in your circuit, and how each of these different kinds of logical operations perform. And some are worse than others. And of course, we're working on improving the ones that are the worst, et cetera, et cetera. And producing a plot like this takes an enormous amount of work. And even so we have to design all of the circuits and simulate them. And that's obviously a lot of work. But even then, there are limitations on what we can do. in order to obtain this data point, for example, we have to build a large code, design the circuit, design the decoder, which processes the circuit and decides what errors should be corrected and how, test how well it's working, and then run it on the order of 10 to the 8 times to get statistics. And that's not even the lowest error regime that we would like to operate this thing. So we want to understand what's happening down here as well, which we cannot run 10 to the 16 times. It's just not possible. So we need techniques to analyze that and to kind of understand how these lines should extrapolate. And that is an entire research program. So the last thing I wanted to do is kind of just show a highlight of what the point of all of this is, which is what could you do with a computer like this, and how does it compare with other approaches? So in order to get a handle on this, I'm going to draw some pictures here, which I want to explain first. So there's a nice paper by Travis Schulten and others that takes most of the algorithms that people have actually mapped out for real problems that people care about. And so they classify these problems into different types. You've got cryptography and you've got like estimation problems, you've got quantum simulation. So there are many problems that they characterize. And what we did, just to kind of get a feel for what you could do with different sizes of quantum computer, is from this information is just draw this convex hull. What I mean by convex hull here is any point in this pink region, there's at least one problem of interest that's in the cryptography category that you could achieve if you were able with your quantum computer to implement that number of T-gates, and you have this number of logical qubits. So for example, if I'm here, then I can definitely implement this problem because I have more T-gates that I can apply than that problem requires, and I have more qubits than it requires, so I can implement it. And so if you're anywhere in this region, then there's some problem that's a crypto problem that is considered of interest, that you could solve. And you can do the same thing for other classes of problems, like there's simulation problems, and physics would probably be the closest thing to things that some people in the high energy community might be interested in. But these problems are kind of just illustrative. And so if you do this, you can, it's not the same color scheme, etc. But that's where these shapes come from here. These different shapes is from that analysis. And then you can ask what capability would you have with different numbers of qubits if you were going to build surface codes, or if you were going to use this approach that I've described here. And so you can, in the largest scenario, if you had 500,000 physical qubits and 10 to the -4 error rate, so this is kind of the most optimistic scale, then you can see that if you had surface codes, so doing everything locally in your hardware, then you would be able to achieve everything down below this on the left. If you used this kind of LDPC architecture, then you would be able to have many more logical qubits. Roughly the same in the Y direction, but many more logical qubits, about an order of magnitude, and it just unlocks a lot more problems that you can then solve. So that's the motivation for this. So these are the people that I worked with on this project that I would like to thank. But yeah, the big picture is this plan that I've proposed at the minute is almost certainly not what we're going to actually build. This is kind of a first pass at trying to work out to dot all the I's and cross all the T's on a plan using quantum LDPC codes, showing that plan would have significant benefits over the surface code. And then over the coming years, this is kind of our blueprint that we work on improving upon. But it is kind of, I think there's elements from this which will probably continue to persist in whatever plan we do end up with. So yeah, that's what I wanted to tell you guys about. That's it.
Thank you very much, Michael. we don't can talk. We already had some questions, but please ask more. And also for the online participants, if you want to ask a question, just unmute yourself. Okay, maybe I'll start with one.
Sure.
Like you showed us this modular picture,
Yeah.
but let's see if now I want to apply a CNOT across two modules. Like one logic qubit here, the other logic qubit in a different modular. Would I do the same type of thing, like the measurement you just described, like with the pivot?
Yeah.
Or with some other.
So the simplest layout that we would imagine for these modules is that each module is connected to two other modules and that they're laid out in a line. So you can imagine this as like a line of chips that are connected neighbor to neighbor. And this is the simplest connectivity that you could imagine. You could have richer connectivity than that, in which case there are better ways of doing things than what I'm about to describe. But this is the minimal connectivity, a line, of course. Like if you break it anywhere, then it's no longer connected. So it's kind of the minimal you can imagine. And what you do in this approach is you use your pivots, or one way to think about it at least, is you use your pivots to produce a bell pair between the two modules that you want to connect.
The pivot from one of the modules?
Yeah, so you have every module has one pivot.
Right.
And your goal is to produce a bell pair between the two modules in the pivots.
I see.
And the way that you can do that, it's quite simple, is you do adjacent pair bell preparation. And then, so let's say you do even odd bell preparation. Then you do, you shift by one, odd even bell measurement. So both of these are nearest neighbor operations, and they can be done in parallel. So it takes 2 steps to do that. That produces a bell measurement on 2 ends. So that's the approach of this kind of scheme, is that if you have nearest neighbor connectivity, then in formal mathematical circuit language, we say it's a constant time circuit to implement a long range operation between 2 qubits, because you just do this trick where you create disjoint bell pairs and then disjoint bell measurements that result in a bell pair across the whole thing. Yeah.
Thank you.
Is it technically more costly, like from the engineering perspective, to have all the modules linked to all the other modules?
I think so, yeah. I think each time you want to connect a module to another module, you need some, in the language that I was using earlier, you need some L couplers between these chips. And L couplers are probably the most difficult thing in the proposal that I've described today that we would imagine building. So you probably want to minimize the number of them. You also, if you just think about the practical issues, if you imagine you have a 2D chip with a grid of qubits on it, and that chip already has these short and long range connections within it, and now we want to connect some of those qubits to other chips, you're going to have some kind of a congestion issue between your connections if you start connecting these chips all to all. Once there's, say, 20, suppose there's 20 chips and you're going to connect them all to all, that means that each chip is now got wires to 20 others, and probably multiple to each of those. And so that just has you have a lot of connections you need to build in.
So the nearest neighbor connectivity is not really going to go away. It's just going to shift from the local qubits to nearest neighbor on module.
I wouldn't go as far as that. So I think the L couplers that have been built, the ones that I described earlier that are at currently 10 to the minus 2-ish error rates, those are like a meter long. So it's not that you can only do nearest neighbor chips. It's more that you should have sparse connectivity among chips. And actually sparse connectivity for these kinds of communication tasks is very good. You can induce, for example, if you have a sparse graph and you want to use this sparse graph to induce a permutation, you can do any permutation in logarithmic depth. It's almost as good as having all-to-all connectivity. Just have sparse if it's random.
Start sparse, but not specifically nearest neighbor.
Yeah, nearest neighbor. Nearest neighbor. The worst case, for the problem I just described of a classical permutation is linear.
I see.
Yeah.
So just a follow-up question.
Yeah.
Between the modules, like, what would be the ideal number of the L couplers?
So what we've assumed here is that the number of L couplers between the chips is, well, I had specific numbers earlier, but it's roughly D, where D is the code distance.
Okay.
So we have these two different scenarios. One code distance is 12, the other code distance is 18. And the number of L couplers is broadly, it's like a few different from that, but it's pretty close to that. But if you had fewer than that, then what you can do is you can slow down your computation and use one multiple times. Because the way that we're thinking about this is these L couplers are getting used all the time. Yeah. And so if you have fewer of them, you can serialize a little bit and still do the same thing. And it may even be the case that they are not limiting in how much they're used, depending on the algorithm that you're running, in which case you might not even pay a price for that.
Right.
You might not have to slow anything down. It might already be slow enough that you can just get away with fewer L couplers.
Right. Okay.
I have another question. Okay,
I can check on that, but you can ask.
Yeah. So my question is, if you have some knowledge of the locality of like physical errors within one of your modules, within one of your chip, does that help you choose the code in a different way? Because it seems like right now the approach is the other way around, where you're picking the best code and then, basically designing a device for that. But if you, at some point, it's going to be limited by what the devices, what devices can be built, right?
Yeah, I think it's a great question. There's this back and forth that happens. Some people use the buzzword co-design, where you basically have a back and forth between the quantum error correction theory people and the device physics people. And that's how I've seen this process iterate, where the people from the more theory background will say, well, we would love if you could do this. And then the device physics people say, well, that's not possible. So what about this? And then they're like, change the code. And so there is a bit of this that goes on. But I would say it's very nascent in this particular space of quantum LDPC codes. So I think there's a lot of interesting room to improve things there, come up with better codes that are designed for particular connectivity that you can achieve well. But you're right. At the minute, in this particular proposal, we first start with the code and then say, how do we build this code? And that's kind of the flow of co-design. It's just like one direction. Yeah.
Martin just raised his hand. So Martin, would you like to ask it?
Yeah. Hi, Michael. Thanks very much. Great talk. So early on, you said that you did a numerical determination of the structure of the code, and this came out to be the best one. Was there a multi-parameter optimization to make this the best one, and also were there ones that were nearby on whatever metrics you chose that were or that were close to meeting the criterion, or did this one stand out by a lot?
Good question. I would first carefully say that I did not do that. So I don't want to take credit for it. And it was actually, in fact, in a previous paper that predated this one where those codes were identified. I believe that Andrew Cross did that analysis, but even that I'm not 100% sure of. What I will say is that there were many, maybe it was Ted Yoder, actually, I don't know. But there were many codes that were identified. And there were different ones that are better in different ways. So there is a table in that previous paper, which I can share with you afterwards, where they basically list the codes that they picked out as being nice codes in different regimes, and 2 of them are the codes that we analyzed in this work. And for our purposes, I think there probably were not a better choice of 2 codes. We wanted to get the distances to be sufficiently good to implement algorithms that were interesting. I think if we'd gone below distance 12, which is the smaller code that we had, probably we couldn't do that with the error rates that we looked at. And the larger code is large enough to do the large algorithms that we wanted to do in the error regimes that we think are plausible. So, but there are other codes that could be better if those 2 assumptions do not end up holding. So yeah, and there's probably codes that were not discovered even in that search that are interesting. So.
Oh, interesting. So were there commonalities that stood out, in the structure, or, I guess I'm trying to understand the physics of the codes. Was there any commonalities in the structure?
Yeah, there are commonalities. I don't believe that the commonalities are well understood, but the codes that I described and another code, which is the distance 6 version, which is kind of good. Good, I shouldn't use that term because it actually has a technical meaning for codes, but that has nice properties, I should say. They all have the same. You remember when I drew these long-range connections for the additional 2 connections you need beyond nearest neighbor in the code? Yeah. They have the same vectors, but they're tiled on different sized toruses. So that's among the very good, the very nice codes. The ones that seem to be stand out have the same vectors, and I don't think there's a good understanding of why that is.
Okay, interesting. Thanks.
Sure.
So when you say, okay, maybe let's not say a good code because you said that has like a particular meaning, but
it does.
I guess when you're like judging how performant a code is, like how sensitive is this to like a particular, right? Because like ultimately you have to simulate this a lot of times and like see how it performs. That requires kind of assuming some kind of error model.
Yeah.
How sensitive is the kind of performance judgment to the noise model that you choose?
I think it's a good question. It's probably more of a research question than something that I can just immediately answer. I think when we simulate these codes, we typically use, even when we do this much more involved simulation, still a very, very idealized noise model where everything fails with the same probability. It's all very theory land, I would say. So yeah, I think codes that look good in these idealized scenarios might not be as good whenever you look at physical constraints, and the opposite might be true of other codes that look like they're not great, but for some noise models, maybe they're actually better than we would initially think. And the way it typically works is we start with a code and ignore the circuit completely and look at properties of the code that are more fundamental to the code itself. And you can think of that as the simplest possible noise model. That noise model is where measurements of your stabilizers or of your checks are all perfect. And all that happens is IID X errors on the qubits. That's in that model we analyze first, and that's kind of the first pass for finding nice codes typically. And then after you have some code that you think is pretty good in that model, you then say, okay, what if I actually used 1 and 2 qubit circuit to implement this and measure all of the checks in parallel, etc. And then you test it there, and you might find that it wasn't as good as you hoped. In fact, that happened for the distance 12 code in this case. The distance 12 means that there's a certain amount of error suppression. Like 12 has a very concrete meaning, which essentially tells you that the smallest error that will cause a problem is the smallest error will be 6 errors that happen somewhere in your system, and that's the fewest errors that will cause you to fail. And then when you actually run it on the circuit, you find that 5 causes it to fail. So there, yeah, this does happen. So it's a great question, but I would say it's very open.
Okay. So you would say, like, I guess getting on the path to a fully functional machine, you would say, like, it's really, you know, kind of like a really like good understanding of noise models beyond kind of some just generic channel parameterization is going to be like a kind of a crucial step.
I think so, yes. And I think that the way that it's probably going to continue to work is when you have when you're trying to find basic ideas, you start with very simple noise model and then narrow down to candidates that seem like they're going to be quite good, and then increase the amount of computational power required by involving more in your noise model, and then do it again. And eventually you'll end up with device physics and see if everything still works well. Yeah. Any more questions?
Yeah, I see no more questions.
Cool.
So let's thank Michael again.
Thank you.